Okay, so I mean, I'm going to be talking about these Bohmian ideas. I apologize for the physicist in advance because I'm not a physicist, so it may be perhaps a bit too simplistic for you. So because I more work within philosophy, but my background with David Bohm is also sort of personal in the sense that when I was fairly young, in my 20s, I got very interested in Krishnamurti, and then through that I found there was this physicist having these discussions, and I was studying in Uppsala philosophy, but then I ended up in the UK because I was so interested with this people were doing, and so in the course of that I got to know David Bohm, and we sort of started cooperating. Maybe 83, 84, we organized a meeting together, and he was like also my unofficial PhD supervisor. One could say that because I was in the UK and then I went to Helsinki for PhD in philosophy of science and philosophy of mind. And so anyway, I did my PhD in 92, and then Bohm read it, and then he died. So either he felt that there's nothing else to do, or else it was so terrible. But anyway, this just coincided, which was of course very sad because we were doing some work together, but then we didn't finish that. But I was very lucky because in 91, just 1 year before Bohm died, he introduced me to Basil Hiley, his colleague. Bohm was maybe a little bit careful not introducing everybody, because I came more from the soft side, and Basil is still this mathematical. Many of you know him, but I'm extremely grateful for that because somehow Basil and I hit it off quite well. I guess Bohm was both philosophy and physics, and of course when he died, then Basil lost, if you like, a philosopher colleague, and of course for me, I just lost this incredible physics teacher, even though I wasn't, just. And so actually we started discussing, and we had published quite a few papers together as well. And Basil is still very active. I think he turned 89 this November 15, just recently, and we'd had a couple of meetings with him this summer, and he's publishing. He's very extremely active, and he even wrote to me last night a WhatsApp message email saying, no reactions to my recent WhatsApp, where he says he's made tremendous progress in his algebraic approach, which is of course difficult for me. So Basil is always happy if he can do things without the wave function, but the wave function is nowhere in sight. So he likes his quantum mechanics like that. Of course, for me, I try to understand what he does, but it's not always easy, and I could imagine it's not easy for everybody else here either. But anyway, so this is sort of just a little bit of the background there. My own work has, of course, been in my PhD was taking this pilot wave theory and Bohm's version of it, and looking how that would work in the philosophy of mind with mental causation. And then I've later worked on this implicate order program. And now, actually, recently I worked on potentialities. So these are these Bohmian concepts. This talk I'll be mostly, I probably say it here. Yeah, well, then I'll just repeat. I'll be probably mostly talking about this, but then I thought I'll not so much about over here, and maybe to end with this implicate order business, depending on how the time is. Okay. And so now I think, of course, David Bohm's work on the foundation of quantum mechanics is today, it's best known as a version of the de Broglie-Bohm interpretation called Bohmian mechanics. And there's Shelley Goldstein's article in the Stanford Encyclopedia. But you see, of course, Bohm himself worked on many different interpretations of quantum theory. And his own preferred version of Bohmian mechanics differs considerably from the version currently discussed in the foundations of physics. And there's, of course, an irony. I mean, among the Bohmians, there have these sort of disagreements. And I kind of learned that I met David Wallace 1 year ago, and we talked about these things. And like he was saying that he's a bit puzzled about this thing that, if somebody doesn't quite agree, then they won't invite them to a conference, and which people are very puzzled. Why not? I mean, God, no, so and so you cannot, and so David Wallace said that, but they can invite him because he's an infidel. He's not a heretic. But if you're a heretic, you will not be invited. And then as we kept talking, then I said, well, David Bohm was the worst heretic in Bohemian mechanics. And David Wallace like that one. So, and I guess you may maybe even today you can understand why, but still this sort of a. But I mean, okay, this is a bit of a polemic comments I'm making there. I know that when I knew Bohm most, this was like after 84, 85, 86, he was actually very, very interested in his 52 theory. And that's, of course, they wrote this book, Undivided Universe, with Basil Hiley about it. So he cared for the theory, and I think he was very happy to see people like Shelley Goldstein and others really start discussing it, because it had been there and sort of more or less ignored, like Finland in the Monty Python song, sadly ignored. And how does it work? Yeah, anyway. Okay, so anyway, I'll get going here. So we will discuss this idea just very shortly about this pilot wave theory, and finally about this implicate order scheme, which is interestingly, Jen and Ismail has recently talked about it, not mentioning the I word, namely the implicate order, because for many people that might be maybe a bit new age or whatnot. But in effect, she's going to be talking about the fish tank and Bohm's fish tank. Let's see if we ever get there. I'm going so slowly, right? So anyway, I mean, of course, before Bohm published his so-called hidden variable, his version of the pilot wave theory, he actually wrote a textbook called Quantum Theory, 626 pages or something like that, when he was still working in the framework of this so-called usual interpretation. Of course, there are many versions of it, but what he was doing was really, even in that book, seeking a physical interpretation of quantum theory. Bohm actually told me that even at that stage, in those years, he was very frustrated about physics. He felt it was too mathematical, and he felt he wanted to do something else. But then there was nothing else for him to do, and then okay, I'm going to write this book, trying to actually understand, give a more, not just this postulates mathematics, but try to express quantum theory in terms of qualitative and imaginative concepts. And this is it's a very interesting and rich book. I mean, I've written a few things, a few articles on small parts of it, and there's still more there. So I would actually recommend, if anybody is not familiar with the book, it's well worth the 10, 15 quid you get it, the Dover edition. Anyway, but you see, if you do these kinds of things, he clearly went beyond the more anti-metaphysical empiricist approach advocated by many in the Copenhagen. Not all. Wolfgang Pauli, for example, he liked this book very much when Bohm published. He did not like the pilot wave theory, but that's another story. So, I mean, just briefly at that. So I think Bohm himself, he thought that in this book, he was presenting roughly the Niels Bohr view, but he got no reply from Bohr when he sent the book, whereas Pauli wrote an enthusiastic reply. I think he realized later on that the view he presents here is in some ways quite close to Wolfgang Pauli's way of thinking of quantum mechanics. And Bohm admits that he started understanding Niels Bohr only in the 60s when he got a research student interested in Donald Schumacher, who was interested in Wittgenstein. And, Bohr is not the easiest to understand, but we'll be learning more about him later today. So one of the issues he takes up here has to do with this notion of the intrinsic nature of quantum objects, where in classical physics, it's customary to think that something has either a particle or wave nature. So, for Newton particles, for Young waves. And although our ideas about the nature of light changed, all along it was assumed that light had some intrinsic nature. But then the idea, the theory, Bohm, and of course others, thinks that with quantum mechanics is changes, and we have to give up the assumption that a quantum object has an intrinsic nature as a particle or as a wave. And instead, these quantum objects can act either like waves or like particles, depending on how they are treated by the surrounding environment. Okay. And so how should we understand these quantum properties if they are not inherent? And according to Bohm, they are incompletely defined potentialities, the development of which depends on the systems with which the object interacts, as well as on the object itself. And so this incompletely defined, we should read this in the ontological sense. We actually, with a Finnish philosopher, we've done a paper which will be published quite soon, but one of the referees was wondering about some of these terms, and I think this is the way we like to read this. And so the way it works, so Bohm acknowledges that this wave function is the most complete possible description of the electron, but it's incapable of defining the general form in which the electron will manifest itself. So the wave function won't tell you, if you like. So rather than the wave function describing definite pre-extinct forms, like a particle or wave, that are revealed, it only describes these potentialities, and which are actualized or become definite only by interaction with the suitable measuring apparatus. So this is it's just this idea of definite and incompletely defined, just trying to get some intuition. Now, the other thing is, of course, that these potentialities are opposing in the sense that actualizing a given potentiality takes place at the expense of another. And so we cannot actualize particle-like behavior in a situation in which wave-like behavior is actualized. Of course, here, if you do unsharp measurements, I mean, you can have vaguely or somewhat vaguely defined at the same time, but here we are talking about making them precise. Either one. Now, here was actually another comment from the referee. One might wonder whether by opposing, Bohm just means something like that when you cast a die and the result is 2, then at that instant, the probability of the result being 4 becomes 0. And I would say that the point in quantum mechanics is that in the experimental context in which you actualized the position, you could not have even in principle actualized momentum. And this is, of course, like Niels Bohr would say that it would be meaningless to talk about momentum in the context where position is meaningful. Now, whereas in the die, both actualizations are in principle possible in the same context or in the same situation. So this analogy doesn't fully capture the quantum situation. Now, of course, we could say that the postulating potentialities like this to quantum ontology, it's a metaphysical move. It's very different from the way, for example, Niels Bohr would characterize quantum reality because he would think it's meaningless to talk about quantum objects beyond what can be observed. Of course, there's a debate whether Bohr was anti-realist or realist, like Henry Folds thinks that he actually was a realist. And I mean, that's kind of an interesting discussion, but anyway. Now, of course, I mean, this is just to show again that in the so-called usual interpretation, there were big differences, and Heisenberg introduces this explicitly Aristotelian notion of potentiality, probably independently of Bohm. And of course, I've added Margenau there yesterday because it would be interesting, like whether there was any interaction between Margenau and Bohm. Of course, Bohm was sort of younger generation, born in 1917, but still. But of course, the trouble with Bohm was that he was sort of both communist and Jewish, so there might be all these reasons not to listen to anything he has to say. So I don't know, but sometimes I'm puzzled when one looks at the history that how efficiently he was ignored over in some periods of his life. Actually, to the very end, but that's another story. Then he actually became a mystic, and that's even worse than being a communist. So the okay. Anyway, so but let's look at some other aspects here. So we've said that it's a kind of apparatus with which the electron interacts, which determines which of these potential aspects prevails. And what he knows, which is interesting, the way he knows is that this also applies in situations outside experiments, for example, with crystals at the bottom of the sea. And so they're already here, although he was kind of in the Copenhagen camp, he is sort of not strictly limiting it to measuring apparatus, which would in some ways perhaps presuppose the human experimenter that for Bohm, this actualization of quantum potentialities is something that can in principle take place in nature independently of measuring apparatus or human observers. But as we see later, you will need a classically describable environment. Of course, the other thing for me, if I'm thinking of a quantum object at the bottom of the sea, I start worrying about this things like decoherence and stuff like that. But anyway, I guess it's a matter of principle for Bohm that suppose you had some suitably prepared particle there and it met this crystal. So it doesn't need, in principle, it doesn't need observers here. Okay. Of course, there's the thing about the probability as well. Another aspect in which way these quantum properties, because they don't. So these develop when the potentiality is actualized. It's not a deterministic process, but rather probabilistic. And this is, of course, where he does this position measurement. Interestingly, I think here, Bohm, this is more of a comment. I think in this book, Bohm sort of feels that he can solve the measurement problem. But there is a price for that, which we can discuss. But this is just, again, something that maybe some of the physicists can even help me or help us here. But anyway, so this is just a typical position measurement where you start with this broad wave-like packet and let it interact with the position measuring device, maybe, I don't know, photographic plate. What happens in the interaction, the wave function is broken up into independent packets, but you find the electron as a particle in only one of these. And so, of course, what that means is that from the wave function, you can only calculate the probability that a given packet is the correct one, which is the familiar probabilistic aspect. But then what he said, but he doesn't really worry. I mean, in this case, here he doesn't worry about the measurement problem, but he has an entire chapter about that in the book, which is an interesting one. But still, that's what I'm not focusing on that here. The observation he makes here is that he would say that the interpretation of the properties of the electron as incompletely defined potentialities finds its mathematical reflection in the fact that the wave function doesn't completely determine its own interpretation. I mean, well, we might wonder what exactly that means, but we could assume that we are in a situation where the electron has not yet interacted with the measuring apparatus. And now, in this situation, the wave function defines two important kinds of probability, one for a position and one for a momentum. But the wave function by itself does not tell us which of these mutually incompatible functions is the appropriate one. And this is a bit like what was, of course, yesterday we discussed this aspect. And you see, this question can be answered only when we design the experimental arrangement and in this way decide whether the electron interacts with the position measuring device or with the momentum measuring device. So here, of course, I mean, this is kind of the role of the observer. I mean, Henry Stapp has written about this. Once we make a choice, then there's a certain partition. And of course, then we can ask, well, are the laws of physics governing our choice, like what the experimental does and the brain operates? And are those classical laws, quantum laws, or maybe some laws we haven't yet discovered? But still still here, of course, one could see that this, if you just believe in the wave function showing unitary evolution and just the one macroscopic world, and it seems that the experimenter is given a interesting role here. Now, let's see, I also talk about some problems here, some puzzling aspects in the Bohm story. And to see this, we could consider again the statement, like, he says things like, separate this aspect as these potentialities latent in the electron. There's our latency. Only now I know this, the first. Latent in the electron and brought out more fully only by interaction with the suitable measuring apparatus. Okay. Now, you see that here it's tempting to ask, well, doesn't the measuring apparatus itself consist of quantum objects whose properties are also incompletely defined potentialities? And if so, how can then sets of incompletely defined potentialities actualize, other incompletely defined potentialities? And you see, now Bohm does not address this question explicitly in the book, but there's a final short chapter in the book, the very final chapter. It's maybe like 5 pages, where he provides a discussion, and I think with that we can evaluate how he would have answered this question. And you see, because now you see our common intuitions about the nature of the micro and the macro and their relation might well suggest that we can derive classical concepts as limiting cases of quantum concepts. After all, isn't it obvious that macroscopic objects consist of microscopic ones? And isn't it customary to think that quantum theory is more fundamental, so that it could be the basis from which classical theory and classical concepts could be derived as a special limiting case? Now, it's one of the fascinating features of the usual interpretation that this is not at all obvious as the case. And let's see how this can be seen in this Bohm's 1951 quantum ontology. Okay. So what Bohm is saying that quantum properties and these potentialities can be actualized only in interaction with the classically describable system, where, as I said, the measuring apparatus is a special case. The system could be a naturally occurring crystal at the bottom of the sea. And the wave function can be used to calculate the probability that we'll get this definite value. But Bohm would say the measuring apparatus itself cannot be understood as a purely quantum object, that is, consisting only of incompletely defined potentialities, for its last stages are always classically describable. I mean, this is in some sense, of course, something you find in Copenhagen, right? Copenhagen invitation. Now, this means that after the measurement interaction, we will find the macroscopic pointer of the measuring apparatus in a well-defined position pointing to a definite result. And Bohm would say it's only at the classical level that definite results for an experiment can be obtained. I mean, this is, of course, very straightforward. Now, he writes then, this means that without an appeal to a classical level, quantum theory would have no meaning. And then this is his own italics. He concludes that quantum theory presupposes the classical level and the general correctness of classical concepts in describing this level. It does not deduce classical concepts as limiting cases of quantum concepts. Okay? And so now what about the correspondence principle? Does it not show that we can derive classical ontology as a limiting case of quantum ontology? No, says Bohm, because the correspondence principle is simply a consistency condition, which requires that when the quantum theory and plus its classical limitation is carried to the limit of high quantum numbers, the simple classical theory will be obtained. So we could say that the correspondence principle is not a direct derivation tool, but a condition ensuring consistency between quantum and classical theories. So this is actually interesting because I tried this on the ChatGPT forum. I asked first ChatGPT for that, can one derive classical physics as a limiting case from quantum physics? And the answer was, oh, yes. And then it gives like 5 or 6 reasons how beautiful it works. Well, then I said, well, then I put in there this quotation of Bohm's book and said, if what Bohm is saying below is correct, then what you said was wrong. And then I said, oh yes, of course. And then it gives a nice, it gives a beautiful 5-point illustration of this, so be careful. But it's like your best friend, whatever you know. Like, should I do so and so? Should I do this? Yeah. Anyway, but let's go. You see, now there's this quote by, you may land down lift shift. They write this thing that quantum mechanics occupies a very unusual place. It contains classical mechanisms, limiting case, yet at the same time, it writes this for its own. I was in this physics founders conference in Italy. I think it's called DICE in September, and at least 2, if not 3 physicists, they have this quote in their slides still. And of course, then if Bohm is correct, then the first part is strictly speaking incorrect, but of course, partly the idea is, the idea is similar there. But anyway, so this sentence lives on. But perhaps, yeah, anyway. Okay. Well, just a few more slides about this. So anyway, so what's implied is that quantum theory needs classical theory as a foundational framework. And this means that quantum theory would be an incomplete description. And the difference is that with quantum, you have these potentialities. In the classical level, you have definite objects and events, which you don't have in the quantum level, according to Bohm, in this model. And the classical properties cannot be deduced, but they must be consistent. So that's just this same point. Now, then we might wonder, well, does the world divide into these 2 independent realms with classical and quantum? And of course not, because they depend on each other. We need these well-defined classical events to actualize quantum potentialities, but also reciprocally, we need quantum theory to fully understand the large-scale behavior. So now we are in a strange situation here, right? So now we see, there's a bit of a Niels Bohr coming up here is like Bohm's take of it, right? That the large-scale and small-scale properties are both needed to describe complementary aspects of a more fundamental indivisible unit, namely the system as a whole. I wonder if Niels Bohr ever used complementarity in this way to characterize the micro and the macro, but anyway. Now, of course, we get this kind of, well, I've called this an interesting ontology because somehow it's just trying to work out what it is. So we have these 2 interdependent levels, which are different in their nature and the tendencies. And at the quantum level, there's a continual tendency for the system to cover the whole range of its potentialities. While at the classical level, there's a tendency for things to become definite, for the specific potentiality to be realized. And then when that happens, well, of course, this level meet, for example, in this process of measurement, where the system settles down to a particle value and all the other possibilities are discarded. And this is like connected to the idea of collapse of the wave function. And so at the end of the process of measurement, there appears to be a definite result where this pointer is pointing to a specific value. But this is reflected back into the quantum level in the sense that the narrowing down of potentialities at the classical level is accompanied by a similar narrowing of potentialities at the quantum level. So if you measure position and get a definite result, it affects this potentiality. It makes also the position potentiality is more narrow at the quantum level. But when that happens for the position, the narrowing, there will be a widening of this complementary variable, this, for example, momentum. which then influences our expectations about what will be observed at the classical level if we now make a momentum measurement. So we have this kind of course, this relationship. And so he would summarize that in the continual interplay between the quantum potentialities and their classical relations, the system is subject to an endless series of transformations. So here we see this again, that it's not something that has constant intrinsic nature, but it is a more fluid or dynamic view. And here I'm going to skip over a little bit toward the discussion. And of course, one might wonder whether it's relevant today to go back to this 51 discussion. And we saw that Bohm himself acknowledged that quantum theory presupposes the framework of classical physics, and this cannot be seen as a satisfactory view for anyone who assumes that quantum theory is a complete description of the non-relativistic domain, okay? But we could say that the fact is that there is still no commonly accepted interpretation. And you see, one way of putting it is that there is no commonly accepted view of the relation between the quantum level and the classical level, and this is why a view such as the many worlds interpretation is taken by many to be a genuine option in the current debates. There is no, to make it more precise, there is no commonly accepted account of how quantum theory gives rise to a single macroscopic world. And thus the idea of many worlds remains an option. And we had actually David Wallace in June in Helsinki, and so we talked, over dinner we talked about a little bit about these things, and I think we kind of, somehow it seemed to me make sense to both of us, but of course after a couple of, I can't speak for him, I can only speak for myself, right? Anyway, so the but this is in a way it still leaves the this Bohmian view that okay, let's see here. Mm-hmm. So given this, if one wants to avoid the assumption of many worlds, it is perhaps not such a bad option to accept that currently the quantum theory presupposes the classical level. And this would be to acknowledge that quantum theory is incomplete and that something new is needed if you want to derive a single unique classical world from the quantum level. And you see, of course, Bohm's later pilot wave theory, which, as the story goes, that Bohm wrote this book, Einstein wanted to talk with him, and so Einstein talked him into go and look for hidden variables and realistic interpretation. Bohm rediscovers the de Broglie theory, does it more consistently, like a theory of measurements there. And here, of course, you get there. And here we get Basil's slide. And the way it works here for the Bohm theory is, of course, that you get this equation, which looks like classical physics with this extra term. And so whenever this, if you can show that this is zero, you get your classical physics. So in this sense, the classical, with some assumptions, you can say that the classical ontology is already there in your quantum theory. Basically, because you've added the particle, not assume that there are particles, and this is what all these. So you already have definite objects at the quantum level, and then what you have to do is to get rid of Q, you get rid of this, and then particles will come in straight lines and behave like Newtonian physics. The active information idea came from here. First, Bohm himself called this quantum potential strange and arbitrary, but then later on he then got excited about this, the fact that the R, which is the amplitude of this quantum field, it only depends on the second spatial derivative, which is the form, and he came up with the idea that actually the way the quantum potential influences the particles is by informing their motion. So, but that idea just somehow hasn't, some people are interested in it, but even many of the Bohmians, they would just reject it because it's a second order theory and that kind of discussion. But I know here in the audience, we have people who have also explored this, the quantum potential approach, but anyway. But I won't spend so much time on that today. I just note here that that given that we don't agree about anything, why not throw in yet another one into the game? And so question is whether this could still be a live option. At least we have seen there's this link between physics and metaphysics with this. If you want to have a scientific metaphysics, or then you get this notion of potentialities. And I know there are other authors who have recently moved to a similar direction. So, for example, these three in this paper, they suggest that quantum theory is best understood as requiring an ontological dualism of res extensa and res potential, understood as mutually implicative ontological extents, and which you can then use to explain non-locality entanglement, null measurements, and wave function collapse. And so they don't refer, this is of course quite common that people don't refer to Bohm's 51. I guess people just don't know about it, that he has this quite a lengthy discussion of potentialities. So usually we think it's Heisenberg who does this. But in these, they make similar suggestions as Bohm did, and introducing the interesting insights. For example, Bohm has a nice discussion of EPR, non-locality, in terms of these potentialities in the book, in the chapter on measurements, they also have quite in this paper. There's quite a nice discussion of this entanglement. Okay. So another thing, if we think of this view of potentialities, it could be a middle way between what I could call very counterintuitive actualist views, such as the many worlds or wave function realism, and on the other hand, the radical epistemic and subjectivist neo-Bohrian views, such as cubism. I mean, of course, all of these are interesting in their own ways, and people give very nice arguments for them. So, but in some ways, I feel Bohm was always a little bit in the middle. He had, like in the implicate order framework, he had something that looks a bit like this wave function realism, but not as radically as you see in the work of David Albert. And of course, even in the pilot wave theory, the trouble is, of course, even for two particles, the wave function lives in this 6-dimensional configuration space, which kind of goes toward this wave function realism. But Bohm himself felt that this notion of, if we say that this quantum potential is like an information potential, he felt the multidimensionality would be like multidimensions of information, rather than having these spatial dimensions, 3n. But of course, he didn't tell what is carrying this information. So it's still, but it's again trying to avoid this multidimensionality in some extreme sense, and so in that sense, I think the various Bohmian schemes they have these exotic features, but he's still keeping a connection to some sort of common sense reality, or our everyday reality. In the implicate order scheme, there's the explicate order, for example. Now, just a few more minutes. I would also say that this idea that the potentialities are, if you like, part of the ontology, it would fit nicely together with these suggestions that both quantum gravity and quantum non-locality suggest the need to consider a non-spatial temporal order from which space-time emerges. And this is, of course, something that Bohm and Hiley and Penrose, they were talking in the 60s. Wheeler talks about the pre-space, which is roughly the same idea as this Bohm's implicate order. And so, and this is, you see, there now you can see here, Yen and Ismail's paper is called What Entanglement Might Be Telling Us, Space, Quantum Mechanics, and Bohm's Fish Tank. So what is this Bohm's Fish Tank? Well, this is something that Bohm came up to illustrate non-locality, where it's an analogy, okay? So there's your three-dimensional fish in a fish tank. You're taking two pictures. A is seeing the fish from the back, and the B is seeing the fish from the side. And when you look at these screens, it may appear that there's a non-local correlation between the two images. And of course, you could make a situation which would look very puzzling for an observer, like hiding the screens and just seeing, here we are. But of course, once you know this underlying reality, it makes sense, because these would be two-dimensional projections of a three-dimensional reality, and therefore what looks as non-local can be actually understood as different aspects of this. So it's a kind of way of thinking of non-locality. This is a picture from Yenan Ismail. She has made a nicer drawing, and I guess she will add some of these other things there. I also did, while we were having dinner 2 nights ago, I did my EPR in this sort of restaurant yogi, because I was sitting right next to the fish tank. I thought this is a sign, some sort of retro causal effect from my talk. That I don't know what happened there, but yeah. Yeah. Okay, there we go. All right. So anyway, I'm ending just with a few quotations from Yenan Ismail's article. What he's saying is about this, he calls these toy models, and then he talks also about some sort of causal networks. In case of causality, what the toy model suggests is a way of hanging on to all the causal relationships that we find in space-time. But instead of looking for microscopic causal processes propagating through space-time, we look for a substructure of connections behind the scenes, threading connections through degrees of freedom that aren't themselves localized in space. And so she would say that just as we can distinguish two notions of causation, we can discern two notions of space. And we use our space to refer to the manifest space of everyday sense, and Ur space to refer to the space in which the fundamental particles are housed. And this Ur space would act as the ground of individuation, or even it would be the level from which the world decomposes into separable parts. I guess if you get your factorization, things like that. And so each of these ways of speaking evokes a role that our space plays in classical physics. I think she refers to Gareth Evans, the way we use space to individuate things. And the question is then whether we should see the kinds of connections that the quantum formalist predicts among local beables in our space as suggesting the existence of a more fundamental ordering. An Ur space containing beables whose connections to space-time observables screens off the internal connections among the latter. So again, this would be like a way of thinking about and now I'll end just with this final slide, is what Bohm, when he published this book, Wholeness and Implicate Order in 1980, and this is a description of the chapter 6. So he says he's gonna go and develop a new notion of order, which fits wholeness, which he calls this implicate order. And there, space and time are no longer the dominant factors, but an entirely different sort of basic connection elements is possible. And from which we get our notion of space-time and also separately existent particles. And of course, then the ordinary notions appear in what is called the explicate or unfolded order, which is a special case. So in this case, one can see already here that this idea of course, space-time and emergent and all that. But I think philosophers of physics haven't given that much attention to the implicate order scheme, but somehow I feel that maybe who knows, maybe through people like Yenan Ismail and others, we'll be discussing that as well. And this, in some sense, I feel that this has a connection to this idea of potentialities as well as a realm. But I think that's about where I'll end. Thank you very much.
I want to apologize, especially to the speaker, but I didn't wake up 10 minutes ago, but I was really impossibilitated to be here before. So sorry for that.
No, that's okay. Thank you.
when I when I hear all the different ideas to try to give an interpretation on quantum mechanics, I feel often more confused than before, because in order to gain some sort of interpretation, people invent more and more unconventional things. They invent sort of things which, and I feel that we have more problems than we had before. After, so now I would like to simply ask you: have you any specific ideas what should be the set conditions for a satisfying interpretation of quantum mechanics? No one seems to really discuss that. Setting up sufficient conditions for interpretation is that and that and that and that. No one takes that, starts on that. What is your opinion about that?
Good. I'll just turn off my light. So, okay, of course, my answer is as a philosopher, not as a physicist, but I would still say, can we do it without assuming many worlds? I mean, I like David Wallace very much and all that stuff, but still, my question is, can we do it without that? Because that's just gets so somehow unplausible. In that case, I feel it comes from thinking that the theory of physics is just mathematics. And then if you assume that, you will end up with many worlds quite easily. But so in some ways, partly I would just say negative things like, can we do it without this and this and this? Now, but that's a very good question, because I think if we took up that question, people would probably have many, many different answers to what the criteria should be. But it's a good question. I mean, maybe I don't know if anybody has ever tried, that could we agree about where the goal posts are? I just think it's terribly difficult to see that. But I won't even try to answer that question, but it's a very good question, and we can talk about it later.
I took a quick look at Bohm's book, and I noticed that he used the phrase latent potentialities even to kind of even show how these three different perspectives that were discussed in the last 2 days about potentialities, how it really is not so clear in the historical record exactly what was the ordering of things. But latent potentialities, the latency and potentiality together. And I actually, like most people, I think, and even in the undivided universe, you find that there's a statement about how Heisenberg uses this, and it's well known from Heisenberg, but people don't know about the Bohm.
Right.
So I thank you very much for reminding us of that fact. I was wondering if you have any understanding of how Einstein's rejection of Bohmian mechanics, after he sort of prompted looking for it, was dealt with later, because one thing that I do recall being the case was that it suggested there were infinite accelerations of particles in this model, and I think that turned one of the things. I think there were a few things that turned off Einstein. That was one of them. So I was wondering if you'd understood from Basel or anyone else what was the reaction to that.
Yeah, I guess if it's a non-relativistic theory, then you would be allowed those infinite accelerations, right? It's an idealization, the model. But no, I don't know so much. I mean, I've tried to check that. Bohm himself said that, I mean, he has written about it, but he also mentioned that he was particularly kind of unhappy about the fact that Einstein didn't give enough support, because if he had, then, perhaps more people would have thought about it. I mean, there's the Einstein-Bohr correspondence where Einstein makes a few comments like it's too cheap, and of course Einstein did write a paper, this particle in the box critique, to Max Born Festschrift, which then I think Bohm was able to answer. So there was kind of he didn't completely ignore it. He actually wrote a paper about it, but I don't know whether it was non-locality or what was really the trouble. But of course, on that note, then Bohm and quantum mechanics sort of won, if we take the experimental results to verify non-locality for those who think there might be such a thing, right?
And
Well, one talked about potentialities or latencies, whether one expects them to behave in a certain way, particularly to obey a certain algebra. So I'm trying to understand your notion of opposing potentialities. I would a priori expect that they do not need to relate in any way among each other. But actually, the opposing potentiality is doing a lot of work here, because it is what distinguishes quantum theory from classical theory to a large extent. So it's just more of a naive question, as in, what does one expect? How does one expect potentialities to behave among themselves?
Yeah, no, that's good. I don't know if I really have thought about it so much. I think one thing at the time when Bohm wrote the book, he was probably already a dialectical materialist. So because he went to Berkeley and with Oppenheimer and all that. So I think that's maybe he was reading a lot of dialectical material literature, and of course the opposites. It's coming from sort of Hegel, the unity of the opposites and things like that. So I think the maybe some there, but of course it has to do with this interesting dependence in this case that we actually in the paper I put over here. This will be published, but it's a surprise to a friend, so I won't tell you where it will be published, but you will find it. You will find it here. You will find it here in maybe like 2 weeks. And here, what we do, Alex Caruth, he's in Helsinki. He's a metaphysician, and so he puts this Bohm's ideas in relation to Martin's, who has similar ideas about potentiality. So I would recommend have a look at our paper when it's published, and then write to us.
so one final question.
So I wanted to ask you, I've always assumed the quantum potential to be inspired by potential energy. But now you're making me think that he may have gotten the name from his earlier discussion of potentialities. And that would give it a different meaning. So the quantum potential would be the repository of all the quantum potentialities, in some sense, that get differently actualized by acts of measurement. And so that would be quite close to a latency interpretation of the observables, I think. If you think about it.
No, that is interesting, but I think you see one thing that Basil highly does these days. He doesn't like too much this simple approach. Sometimes he calls this the Mickey Mouse version, which of course offends a lot of his students who have done a lot of work to develop it. But anyway, with Basil, he's looking at the history, reading papers right here and there, Feynman, Dirac. He always finds the quantum potential all over the place. And Basil's argument that it's at the heart of quantum mechanics. It's not just some artificial add-on. And he got very excited when somebody discovered that in 1952, in Physical Review, a little after Bohm's paper, Bruce DeWitt has a paper where he also has this quantum, I think he may call it the quantum mechanical potential, which there does something, I forget exactly what, but to get covariance or something like that. So in that sense, my feeling would be that a lot of people have discovered this thing, and a lot of people have discovered that it has the dimensions of energy and it's some kind of a potential. So whether or not Bohm has any, when he chooses this term, the quantum potential, whether there's any connection to this potentiality, I don't know. Because of course here in some sense, this is very, very different, because here you have the electron is an actual. The way potentiality comes here is that if you think of this as an information that's like all over the place, like in this case, the electron is coming and the information is actually active where the electron is. But then Bohm would say it's potentially active in all the other places, meaning if a particle was there, it would experience this potential. So there's a kind of connection, but I think the term, if I had to make a choice, I would think that they are thinking about this as more like a potential energy and not potentiality. Thanks.
All right, thank you very much.
Thank you. Thank you.